Kia ora everyone. Welcome back. Welcome to, it says week 2, lecture 2. There's a typo there already. This is week 1, lecture 2. The material here is in the textbook in ZIL, sections 1.1 and 1.2. And today we're going to be looking at solutions of ODEs, solutions of differential equations. What does that mean for a function to be a solution of a differential equation? And when do differential equations even have solutions? So, not going to say how to find the solution, but how to tell when you've got one. So let's just do this for an example. A solution of a differential equation, it's a function which satisfies the equation when you substitute it into the equation. So here's the example differential equation we did last time. And we claim that y equals 3e to the 2x is a solution. So let's check that. Is it true that the derivative of this function is equal to 2 times the function? We just plug that function y into both sides, substitute it in. Its derivative is the derivative of 3e to the 2x. That is 3 times e to the 2x times 2 by the chain rule, so you'll get to brush up your calculus again. So that was the left-hand side, and the right-hand side is 2y, which is 2 times 3e to the 2x. So this one is 6e to the 2x. This one is 6e to the 2x. They are equal. So this function satisfies the differential equation, so it's a solution. Now it turns out this differential equation will have other solutions. It's going to have lots of solutions, but at least we've found one. Now, it won't always be so easy that you get y equals a function of x. Sometimes you can't write the solution in the form y equals some explicit function of x. But you can get the next best thing. You can get the solution in the form some function of x and y equal to 0, where this function of x and y could be really complicated so that you can't actually solve it to get y equals something. So something like this is called an implicit solution. Something like this is called an explicit solution. So the explicit solution is of course better, but sometimes you can't get it. So let's have an example of an implicit solution. Here's a differential equation. Dy dx equals minus x over y, and we claim that x squared plus y squared minus 1 equals 0 is an implicit solution to this differential equation. Now, this isn't a very complicated example, so that one is not too hard to solve for y, but just we're not going to do it that way. Let's check that. Take this g of x and y and differentiate it. The derivative with respect to x of x squared plus y the derivative of the right hand side is 0. Now I do the derivative of the left hand side, I get 2x plus. Now how do I differentiate y squared? Here you have to remember that y is implicitly a function of x defined through this equation. So you differentiate with the chain rule. I could actually write that like y of x squared minus 1. So its derivative by the chain rule would be 2 times y times the derivative of the inside function, which is dy dx. The derivative of negative 1 is 0, right hand side is 0. Rearrange it and you get dy dx equals minus x over y. So even though I never got a formula y equals a function of x, I have checked that this implicit solution does satisfy the differential equation. So what is this solution graphically? I've run out of space here, so I'll just clear off a little bit, because you might recognize this. x squared plus y squared minus 1 equals 0, put the 1 on the other side, you get the equation x squared plus y squared equals 1. It's a circle. And you can't, the complication here is that for each x value, if you fix x and try and solve for y, there's two solutions. There's that one and that one. So this single implicit equation, if you try to solve for y, you get two different solutions, each of which would separately satisfy the differential equation. So it's much easier to simply write it in this implicit form. So we'll see examples of this quite soon next week, where this is implicit solution is the most natural way to write this solution. As I said a second ago, normally when you solve a d, you don't just get one solution, like that dy dx equals 2y. It has lots of solutions. It has arbitrary parameters. And in fact, if you had an nth order ordinary differential equation, you would get n arbitrary parameters. So let's again take this simple differential equation. Y equals any constant times e to the 2x is a solution for any value of the parameter a. And in fact, it wouldn't be too hard to show. We'd be able to show that just in a lecture or two, that this is in fact all possible solutions of the differential equation. Well, let's check it. dy dx equals a times 2e to the 2x equals 2y. Simplicity itself. I could graph those solutions. If a is equal to 1, I'd get e to the 2x. If a was equal to 2, I'd get 2e to the 2x. If a was equal to 3, like I had before, I'd get 3e to the 2x. If a was equal to 0, I'd get a particularly simple solution, just y equals 0. That's also a solution. A equals -1, a equals -2. So the different solution curves correspond to the different solutions, and taken together, you don't just get one curve, you get a whole family of curves. They fill out the whole plane, so that through each point in the plane there is a solution. So this thing here, with the constant in there, or the parameter, that's called the general solution. If I tell you something more about the solution, like which point it goes through, then I can find the value of that parameter. So if also y of 0 equals 3, I want the curve that goes through the point y equals 3 when x equals 0, then I can substitute that in, and I get, plug in x equals 0, and I get 3 equals a e to the 2 times 0. E to the 0 is 1, so a is 3, so y is 3e to the 2x. So that would be called the particular solution. Particular solution. So the general solution is a family of functions which gives you all possible solutions to the differential equation. If you have some extra information, then you can plug that in and find which particular solution you want. That's the particular solution. So, putting that together, a first order initial value problem will look like this. There will be some function of x and y and dy dx equals 0, so some big complicated differential equation on the left. So some function of x and the unknown function and its derivative all equaling 0, together with y at some point x naught equal to y naught. That is called an initial value problem, or IVP. And as we'll see, if you have a higher order equation, then you'll have more arbitrary parameters and you'll need more initial data to find the values of those constants. So a second order initial value problem will look like this: some function of x and y, and the first derivative of y with respect to x, and the second derivative, some big complicated mess involving all of those things. And now I need two pieces of information, and the simplest way is to specify the value of y and its derivative at some point. And those equations all together form a second order initial value problem. Okay, so I've been doing that example dy dx equals 2y to death a little bit, so here's a slightly more complicated one. So in this example, show that this function, so it's a family of functions with a parameter a in it, show that this is the general solution to this differential equation. So that's a first order linear ordinary differential equation, telling you what the solution is, so that's a bit of a help. And then find the particular solution that also satisfies the initial condition y of 0 equals 0. Sketch the graphs of the families of solutions and also the particular solution. So again, you know enough now to have a go at this. So pause the video, see what you can do, then restart it, and we'll look at the solution. So that even if you get stuck, just spending a few minutes working on it by yourself will be extremely useful for your learning, because then when you see the solution, you already have been thinking about it a little bit. Okay, let's do this problem. I need to take that function y and plug it into that differential equation. So I need to work out dy dx minus y and see if it comes out to equal x. Well, what's dy dx? Let's just differentiate that function. The derivative of a e to the x is a e to the x. The derivative of minus 1 is 0. The derivative of minus x is minus 1. That's dy dx. Minus y, well, y is a e to the x minus 1 minus x. That a e to the x minus a equals to the x. Minus 1 minus minus 1, that cancels. I've got minus x, that is x. So it does satisfy the differential equation, so I'm done. So that was the general solution. Now I want the particular solution that also satisfies y of 0 equals 0. So I substitute x and y equal to 0 into the solution, and I get 0 equals a e to the 0 minus 1 minus 0, which is a minus 1. So that's the value of y, and that must equal 0. Well, actually I've said that already. So 0 equals a minus 1, so a is 1. So the particular solution is y equals e to the x minus 1 minus x. Then it says, sketch graphs of the family of solutions and sketch the particular solution. And I run out of space a little bit. No, oh yes, there's a bit more space. So here we go. Y equals a e to the x minus 1 minus x. Let's do it the old-fashioned way, by hand, not with a computer. Well, there's a very simple one to sketch, which is when a is 0, then I just get minus 1 minus x. So I'll do that one first. That part where, and that's a straight line, y equals minus 1 minus x. Passes through 0, negative 1. Maybe the next one to sketch is the particular solution I found. That's a equals 1. So I have to take, I get e to the x minus 1 minus x. So I have to take this curve and add e to the x to it. Remember what e to the x looks like. It's very small here and very big over here. And I know that when a is 1, I'm going to be passing through this point here, because I knew that y of 0 was 0. So this is going to look like this, and then getting very big. And then when a is 2, it's going to look something like that. So all the curves altogether will look like that. When a is a half, it's a bit hard to draw. Oh. It's going to look like that. And when a is negative, I'm going to be on the other side. So I get a whole family of curves that fill out the plane. And the one particular solution is the one that passes through this point here. So this one is the particular solution. Of course, if it's a slightly complicated function of x, it can be hard to sketch the graph of that whole family of functions. Notice that they don't cross, so it's a family of curves that fill out the plane smoothly. The other thing to do would be to plot them in MATLAB or Octave, and that's a very easy way of visualizing all the solutions. Okay, thanks everybody, and I will see you at the next lecture.